Next, we're going to talk about strings and tries. These are combinatorial objects that have really come under scrutiny because of computational applications, but they're very well suited to the analytic techniques that we've been talking about. Again, we're in the second half of the class, and this is lecture 8, and we're going to look at these data structure, these combinatorial objects as unlabeled classes mostly, so we'll be talking about OGFs. And again, we'll give some examples in lecture, but there are many more in chapter 8 of the book. So first thing we're going to talk about is bit strings with restrictions. And we did some examples of this as our motivating examples for the analytic combinatorics in lecture 5. But what we'll talk about today is answering questions like this. So this is a number of random bit strings of 70 or 80 bits. And I've got highlighted in there the first occurrence of 000 in each bit string. So a natural question is, what's the expected wait time? That is, how many random bits do we need to see before we get to 000 in a random bit string? Some of these bit strings have no 000s. I think, well, maybe not. But if you look at shorter ones, like at this distance, then there'd be no 000. So the question is, what's the probability that you don't have 000 in an n-bit random bit string? And questions like this actually have lots of important practical applications where the zeros and ones correspond to electrical signals, and certain kinds of devices can't take long strings of offs, for example. Let's review what we talked about for the symbolic method for bit strings. It's one of the very simplest examples of analytic combinatorics. How many binary strings are there with n bits? Of course, they're 2 to the n. And we can do that with the symbolic method by constructing this class of all binary strings B as a sequence of 0 or 1 bits. And then our normal symbolic transfer takes Z0 plus Z1 to 2Z and sequence of anything of 1 over 1 minus that. So that tells us that the OGF that enumerates the number of binary strings is B of Z equals 1 over 1 minus 2Z. And so the coefficient of Z to the n in that is 2 to the n. That's our basic construction for binary strings using the symbolic method. And then we had an alternate way of expressing the same thing. If you say that a bit string is either empty or it's a bit followed by a bit string, a recursive definition, then you get down to the same result. In this one, generalizes to help us answer questions like how many n-bit strings have no 2 consecutive zeros. And again, using the same reasoning, we can say that a bit string with no 2 consecutive zeros is either empty, or it's a single zero, or it's a 1 or a 0, 1, followed by a bit string with no 2 consecutive zeros. That's the natural construction for this class of combinatorial objects. And then that translates through the normal translation theorem to this OGF equation. 1 plus z plus quantity z plus z squared times b0 z. And then we can solve that and we get a polynomial, ratio of 2 polynomials for the generating functions. And our asymptotic, that's a classic example in asymptotic analysis. The coefficient of z to the n in that function is going to be, well, in this case, it's exactly the Fibonacci numbers, but in general, if it's any polynomials, you look at the largest root of the polynomial in the denominator, and that gives an asymptotic expression for the coefficient of b to the n in that generating function. So simply by finding the appropriate root of the polynomial, we get the asymptotics. And for any polynomial, it's going to be the form of constant times the root to the nth power, unless there happen to be multiple roots. So in this case, the it's the golden ratio, phi to the nth power, and then the constant also is explicitly determined. So that's the example that we did in Chapter 5. So first thing we want to do today is extend that. How many binary strings have no runs of p consecutive zeros? And that's going to extend in a natural way, very much like the derivation that I just did. So the construction then is a string with no runs of p consecutive zeros is a string of zeros of length less than p, followed by either an empty string or a 1 followed by a string with no runs of p consecutive zeros. So that's just a generalization of the construction that I did on the last slide. And again, that immediately translates a string of zeros of length less than p is 1 plus z plus so forth up to z to the p minus 1. And then e translates to 1 and z bp of z. And so solving that equation gives bp of z equals, again, a ratio of two polynomials. And again, the coefficient of z to the n in that is asymptotic to a constant times largest root to the nth power, where that dominant root is something we can calculate, and also the coefficient is explicitly available. So this no runs of p consecutive zeros comes down to finding the dominant root of that polynomial 1 minus 2z plus z to the p plus 1. And this is using the SAGE mathematical system to just find those roots, and you can use any system that you want. And I didn't calculate the constants, but let's look at, so anyway, those are those results. Now let's look at what we can infer from that result. So this is a summary of where we were for consecutive zeros. The OGF, S sub p of z, is going to be the sum on n, the number of bit strings of length n with no runs of p consecutive zeros times z to the n, and that we have an explicit formula for that OGF, 1 minus z to the p over 1 minus 2z plus z to the p plus 1. Now, this is similar to the situation we had with permutations. We can convert that into a probability by evaluating at appropriate value of the argument. If you look at SP of z over 2, then the z to the n becomes 1 over 2 to the n, z over 2 to the n. So what that is the probability that a bit string of length n has no run of p zeros. That's a PGF. Just by evaluating the argument at z over 2. So now if we take z equals 1, then that's just summing the, what is that? That's the sum on n of the number of bit strings of length n with no runs of p zeros divided by 2 to the n, which is the sum on n, the probability that the first n bits have no runs of p zeros. And that's the same as the sum that of the probability that the end of the first run of p zeros is bigger than n. So number of bit strings of length n, no run divided by 2 to the n. That's a probability that the first n bits have no runs of p zeros. And that's the same as the probability that the position of the end of the first run of p zeros is bigger than n. But that's exactly the average position of the end of the first run of p zeros. So that's the average wait time. So this argument just gives us these two theorems. The first one is the probability that an n-bit random bit string has no run of p zeros is the coefficient of z to the n in SP evaluated at z over 2. That's the second line here. And so going from the solution on the previous slide, it's going to be our dominant root divided by 2 to the n. And then the other thing is the expected wait time is just our generating function evaluated at 1/2. If you evaluate that generating function at 1/2, you'll see that all that's left, the 1 minus 2z, cancels out. So it's 1/2 to the p plus 1 in the denominator. So it becomes 2 to the p plus 1 minus 2. So that's using the symbolic method to get information, explicit version of the generating function, and then evaluating that generating function to get the analysis of the properties of the consecutive zeros in a random bit string. Just to summarize, for small values of p, which are usually what's of interest, so that's our generating function when p equals 1 is 1 minus z over 1 minus 2z plus 2 plus z squared. So the probability of, approximate probability of no 0 in a random bit string of size n is 1/2 to the n. And then 10, it's 0.0010, and 100, it's 10 to the minus 30th, and the average wait time is 2. For 3 zeros, then we can do the explicit, those are the values of the roots, and it turns out that probability of no run of 2 zeros in 10 bits is about 0.14, and 100 bits, it's 10 to the minus 9th. And the wait time for the first run of 2 zeros is about 6. For 3 zeros, now probability of no run of 3 zeros is becoming more and more likely. So for 10 bits, it's about even chance that there's no run of 3 zeros. For 100 bits, it's still fairly unlikely. 4 zeros, now 10 bits, 3/4 of the time you're not going to have 4 zeros in a row. You have to wait 30 bits to get your first run of 4 zeros on average. But for 100 bits, it's still pretty unlikely that you won't have 4 zeros in a row. And then for 5 zeros, now it's almost 90% chance that you're not going to have 5 consecutive zeros in 10 random bits. 20% chance you're not going to have 5 consecutive zeros in 100 random bits, and the wait time is 62. And then for 6 zeros, it's almost certain, and there's even chances in a string, a random string of 100 bits, that you won't have 6 consecutive zeros. And your wait time is over 100, it's 126. So those are facts that we can derive from this analysis. And actually, this type of statistic is one way to test whether a set of strings is random. In fact, it's always worthwhile to validate these types of mathematical results. And in a situation like this, when it's so easy to write code to validate these results, we should go ahead and do it. So this is a Java program that takes as argument a size n and a number of trials. And what it's going to do is it's going to, this one actually reads the bits from standard in. So we separate out what the bits are from analyzing them. So this will read W bits at a time from standard in. So like in that example, W was 75, and there were a bunch of occurrences of 75 bits that were supposed to be random. And then for each P, it'll check whether there's P consecutive zeros, and then it'll just print out the empirical probabilities. And then this is just the code to just check for P consecutive zeros. So this is a very straightforward program that reads in a bunch of bit strings and then prints out the, out of all those bit strings, what's the empirical probability that you find 1, 2, 3, 4, 5, up to P consecutive zeros. And so for the example that I used on the first slide, this is the data that it gives. And so actually those are the first line of 10,000 bits, 10,000 bit strings of size 100. And for those bit strings, those are the probabilities that 0, 1, 2, 3, 4, 5, and 6 zeros occurred or not. And those compare very favorably with what we just saw was predicted by the theory. So we can think that those bits are past this test for randomness, or we can think of this as validating the theory that we just derived, predicting, for example, that you have a 45% chance of finding, say, 6 consecutive zeros in the random bit strings. Okay, so that's a fine generalization of the simple example that we did for how many bit strings don't have 2 consecutive zeros. So check. So now the next thing that we want to do is consider other specified patterns. So say it's not 0, 0, 0 that we're interested in, but say 0, 0, 1. So now in blue you can hardly see, but the wait time for 0, 0, 0, that's the one that I did before, is in red, and it's an average about 18 for these. But in blue is the wait times for 0, 0, 1. So in the first line, the first occurrence of 0, 0, 1 is starting at the 9th bit, and the second it's at the 4th bit, and so forth. And this time, the expected wait time for 0, 0, 1 in this set of bit strings is only 6. It's much, much less. And now we're wondering, are these bit strings really random? What's going on here? Well, the fact is that the pattern itself definitely is a factor in what the wait time is, and that's what we're going to look at next. So we showed before that the probability that an n-bit random bit string doesn't have 4 zeros in a row is about 0.96 to the n. And the expected wait time is 30. And the question is, does that same thing hold for 0001 or any other pattern of 4 bits? And the answer is no. So in every one that we did, the 001 occurs much earlier than the 0000. So it's a little intuition behind that. So let's say, consider the first occurrence of 3 zeros in a row. The next bit could be either 0 or 1, so our 2 patterns are equally likely once we found 000. But the thing is, if we were looking for 000, then that would mean that we're looking for 4 zeros, and we didn't find it. It would mean that we have 0001 in our bit string, and we're going to have to wait at least 4 more bits before we could find 000. But if we were looking for 0001 and we had a mismatch, it'd mean that there's 4 zeros, and the next bit could give us a match. So if we're going from left to right looking for these 2 patterns, it's not surprising that we're going to find 0001 first. If we find 3 zeros in a row, we get a good chance of being the next bit. But if we're looking for 4 zeros in a row and we find 3 zeros, then we're going to have to wait a long time for the next bit. That's the intuition behind why it occurs much earlier. But now we want to answer this question: what's the probability that a random bit string doesn't contain that pattern, 0001? It's a little bit counterintuitive that it's not the same for any set of 4 bits, but it's definitely not, as we'll see. Or what's the wait time for the first occurrence of 0001? And what about other patterns like 1110 or 1111 and so forth? The idea that it's the pattern itself that determines the probability of existence and the expected wait time has to do with a phenomenon called autocorrelation. That's what we're going to look at next. So what we'll do is use the symbolic method to get explicit equations for the generating function for number of bit strings not containing a specified pattern. It's remarkably easy to develop such an equation with the symbolic method. So what we'll say is we'll take any pattern, P, so it's a pattern of bits, and S sub P is the binary strings that do not contain that pattern at all. And then we'll define T sub P to be the binary strings that end in P and have no other occurrence of P inside. So that's two well-defined sets of bit strings. And so what we're going to do is have two different constructions that relate these classes of bit strings. So the first one is based on the following observations. These two sets are disjoint. That is, the T sub P has the pattern in it, S sub P does not have the pattern in it, so there's no string that's in both of them. Empty string doesn't contain the pattern, so it's in S sub P. And the other thing is, if we have a string in S sub P and we add one bit to it, either we're going to get a string that's in S sub P, or that bit will complete the pattern and we'll get a string that's in T sub P, the only occurrence of the pattern. So based on those observations, we have this symbolic equation or construction that relates these classes of strings. S sub P plus T sub P is either empty or it's S sub P with a bit added. So that's the first equation. And here's the second construction that relates these two combinatorial classes. It's based on the idea of what's called an autocorrelation polynomial. That is a property of the pattern. And the idea is we take the pattern in black and then slide the pattern to the left over itself. And so, well, at the beginning, the pattern matches itself. And the number of trailing bits we use as an exponent, so we start out with a z to the 0 on the polynomial. And then we slide over 1, 2, 3, 4, 5 positions. And when we slide over 5 positions, then the trailing bits match the leading bits of the pattern. Well, the 1, 0, 1, 0 at the beginning match the trailing 4 bits. And we've slid 5 positions, so we put z to the 5th. And then 2 more positions, the 2 trailing bits match the 2 leading bits, that's z to the 7th. So in all the possible slides, the only match of the trailing bits with the leading bits is at positions 0, 5, and 7. That defines the autocorrelation polynomial of the pattern. For this one, its autocorrelation polynomial is 1 plus z to the 5th plus z to the 7th. And that's going to play a role in the development of another relationship between the two combinatorial classes we just defined. This is the second construction. So remember, S sub P doesn't contain the pattern, and T sub P ends in the pattern but has no other occurrence of the pattern. And so the idea is if you take any string in T sub P, and then you add a tail corresponding to the tail that you'd get to complete the pattern in the autocorrelation. So the first one's null. On the second one, if you add the 5 bits that you shifted off at the end of the pattern, you get an occurrence of the pattern. And again, if you add the 7 bits, you get an occurrence of the pattern. So in those 3 cases, null, one corresponding to each bit in the autocorrelation polynomial, you'll get a string that, if you have a string in S sub P that does not contain the pattern, if you add the tail, if you have a string in T sub P and you add these tails, then you'll get a string in S sub P from knocking off the pattern. So every time the result is a string in S sub P followed by the pattern. So S sub P times the pattern is T sub B times the one place for each bit in the correlation polynomial. So that's going to give us the combinatorial construction. So we have those 2 constructions. One, if you add a bit to a string in S, you get either a string in S and P. And the other one is if you take a string in T and you got a chance for every bit in the autocorrelation polynomial to make a string in S followed by the pattern. Those are the 2 constructions. And these these 2 constructions are set up for the symbolic method. They just use the basic operations, so they immediately correspond to generating function equations. First one, z0 plus z1 is 2z, and otherwise it just directly corresponds to the adding the generating functions. In the second one, the pattern has OGF z to the p, so sp times z to the p equals tp, and then what's left over here is the correlation polynomial itself. So now we have two equations in S and P that we can solve, and the correlation polynomial of the pattern is part of the answer. So that's the solution of those two simultaneous equations. This is the OGF for the class of binary strings that contain no occurrence of a specified pattern. Now for any particular pattern, we can plug in the correlation polynomial, and again we have a ratio of two polynomials. We find the dominant root of the one in the denominator, and our count is asymptotic to that root to the nth power multiplied by a constant that we can compute explicitly. So this is a methodology that's going to work for any pattern at all. So here's the end result for 4-bit patterns. Of all possible 4-bit patterns, actually there's only 4 different possibilities for the autocorrelation, it turns out. That classifies the 4-bit patterns. With those autocorrelations, they all start with a 1, and those are the autocorrelations that can come up. And so those lead to these different OGFs. And so they all have different dominant roots. And I didn't compute the constants here. They're all pretty close to 1. And then you can see that this one with 1, 0, 0, it's a slightly smaller number. When we raise that number to the 10th power, we're going to get a smaller number. And for 100th power, it's going to be much, much smaller. It's interesting and maybe counterintuitive, but these are the results. You're going to wait about twice as long for 4 zeros or 4 ones as you are for any one of those 6 patterns. Or another way to look at it is that 0, 0, 0, 0, 4 zeros is 100 times more likely to be absent in a 100-bit string than all of these other patterns, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. So studying this table maybe is a good way to win some bar bets, perhaps. It's kind of surprising that we can so completely characterize this problem with analytic combinatorics. That's the study of bit strings with restrictions, and these studies extend in various ways.